End-to-end testing sounds like a great idea, but it's really not. The problem is that for anything other than simple systems, end-to-end tests can be big, complex, fragile, and don't really control the variables enough to allow you to take proper control of your system under test, and so properly test it or understand the results. On the other hand, thoroughly testing your system in production-like test environments and in life-like scenarios is a great idea. So how are these two ideas different, and how do we achieve the good one while avoiding the traps of the bad one? Oh, and it probably depends on what you mean by end. Hi, I'm Dave Farley of Continuous Delivery. Welcome to my channel. And if you haven't been here before, please do hit subscribe. And if you enjoy the content today, hit like as well. What most organisations mean when they talk about end-to-end testing is testing the whole system in some environment that is a mirror of production. This is a good idea. We want to be able to test the deployment of our system in a lifelike setting, checking things like its configuration and any infrastructure changes that might affect its behaviour, as well as validating that the new features that we've added actually work and reassuring ourselves that we haven't broken anything that was working before. The trouble is, how do we do that? The most common version of end-to-end testing that I've seen in practice is to create something that's often called a staging environment. The idea of this, particularly in teams building big software, is to maintain a kind of shadow copy of the production system. A team works on some changes for their system, and then as part of the release process, they're required to deploy the new versions to the staging environment before release, where they will be evaluated, usually with manual testing, alongside every other team's new versions to check that everything works together. Often, all of this is carried out by people in teams that had nothing to do with the creation of the software. The ops people deploying the changes probably haven't seen them before. In seriously dysfunctional teams, they may not even know what the changes do. Testers in places that test this way are usually paranoid, and with some good reasons. So they test everything. This is slow, expensive, and doesn't give a very high quality result. The testing has happened too late to help build quality into the product. It's just used as a gatekeeping process to hopefully catch the biggest mistakes. The testers have good cause to be nervous, as I said, because the chances of something going wrong at this point are really quite high. If this is the first time that the pieces of the much larger whole are brought together, it's highly unlikely that everything's going to work seamlessly. However diligent the planning, the ways in which software and the people who build it can screw up are many and varied. In organisations that work like this, they're almost inevitably working very slowly. So the gap between each release and so each end-to-end integration test is usually weeks or months. That means that the amount of change going into each release is huge, which means in turn that the chance of something being wrong increases, and the costs of finding it and correcting it when something does go wrong goes up exponentially with the number of changes too. There's another problem. If we are working on a system like this, and we are working on Team B, the kind of system that is downstream from System A and upstream from System B, and this is the only way that we test, then we can't test System B properly at all. If we want to do a good job of System B, then we'd like to test it when it's facing difficulties, as well as when everything's working smoothly. We may like to see, for example, what happens if System A sends our system garbage. But we can't do that if there's a real System A in place. It's not sending us garbage. We'd probably be interested to know how our system copes when it can't establish a connection to System C or loses that connection. But if the connection is working fine, we can't test this either. These are symptoms of a deeper, more fundamental problem. The bigger and more complex the system, the less thoroughly we can test it, because we've lost control of the variables. System A and System C are changing, and we don't know how. And because this big end-to-end thing is so complex, anything that we do is at arm's length. I once joked that this was a bit like eating spaghetti through a letterbox with chopsticks. We really don't have much visibility or much control. If we're primarily interested in testing our system, System B, then we need to do a lot better than this. The key idea here is test isolation. A good test is deterministic and atomic. It's going to put our system under test into a precise, predictable state, the state that we need it to be in order to run our test. And every time that we run this test for the same version of the software, whatever the circumstances, whatever the time of day, whatever else is going on in the system at the same time, we want the same result every time. To maintain the stability of our test, we'd also like it to do that without relying on anything else outside our test and the system that it's testing. We want our test to be targeted and specific. Actually, more formally, I recommend that tests should be concise, accurate, understandable, and durable. They need to be concise so that they aren't too much work to create and clearly focused on a single outcome. They need to be accurate so that they can clearly specify what the system ought to do. They need to be understandable so that we can use them to help everyone associated with the development of the system to understand what the system needs to do, and that this test, if it passes, says that it does it. And they need to be durable, meaning that these tests aren't easily broken by changes to the system. In fact, in my preferred approach, these tests will never be wrong because of changes to the system under test. They may fail when the plumbing breaks, but then we can fix the plumbing. But they're only wrong if the users no longer want the thing that the tests assert. How does all this relate to end-to-end testing? Well, if we drive the behaviour via System A here, then we need to know how to get System A into the correct state so that it will send the information that we're really interested in to our system. That's not likely to be an easier thing than just sending the information that we're really interested in direct to System B. So it's not very likely that our test will be simpler. I'm probably cheating a little bit here because with my preferred approach, you can usually hide a lot of this complexity so that the test cases themselves may still be concise, but the test infrastructure and test data will inevitably be more complex and so harder to maintain. Our test won't be as accurate because we've lost the ability to precisely control the state that System B is in. The only way that we can do that is by guessing where our system ends up after the external system talks to it, or breaking encapsulation by digging in and looking at or changing the private state. I see this second failure a lot. It's a really bad idea because it immediately couples the tests to the system under test, so they break all the time and are much more difficult to maintain. If we're testing end-to-end in this way, our tests are unlikely to be understandable either, because when we're writing them, we're probably worrying about interacting with System A or System C instead of thinking about exactly what it is that we want to learn from our system. Again, you could probably make understandable tests with my preferred DSL-based approach, but you probably won't. Finally, these tests are definitely not durable. Simply by the act of adding Systems A and C into the mix here, we've increased the amount of places where stuff can go wrong. These sorts of end-to-end tests are notoriously difficult to maintain as in a stable, reliable suite. What we'd really like instead is to deploy our system so that as far as it's concerned, it's in production. Same infrastructure, same configuration as far as makes sense, and using the same deployment mechanisms. Then we'd like to connect it to a test rig of some kind. Test infrastructure that allows us under test control to put our system under test into exactly the state that we'd like it to be in, communicating through its natural existing exposed interfaces. Then we invoke the behaviour that we're interested in testing, and we'll collect the outputs from our system via its natural outputs and make assertions on them. So these kind of tests are black box tests that run through the exposed interfaces to our system, but where the tests fake all necessary inputs and collect resulting outputs. We replace System A and System C with fake versions of them, so that we can more accurately control our system under test. So I guess these tests are end-to-end as far as our system is concerned, but not as far as systems that are outside of our control and responsibility to test. So one of the important decisions to make when automating your testing is to decide what constitutes our system. What part of the system are we responsible for and responsible for testing? Continuous delivery helps with this decision. My preferred quick way to describe continuous delivery is that we work so that our software is always in a releasable state. So what does it take to decide if our software is releasable? That's obviously specific to each system. But one thing is for sure. If at the end of evaluating your change, you or someone else has more testing to do before release, then it's not releasable. So the standard here is that if your deployment pipeline says all is good, you should be happy to release into production without any more work. So the scope of a deployment pipeline is a releasable unit of software, whatever that means for your system or subsystem. And acceptance tests are by definition designed to determine if your software is ready to release. So the acceptance tests test a releasable unit of software too. They confirm that everything in the deployment pipeline works as expected. So these tests are kind of end-to-end tests, but only for our software, not for anything else. What this means is that we can test every aspect of our software, including things like its deployment, configuration, and changes to the infrastructure on which it depends, but without testing any software that's outside of our direct control. To do this, we fake interactions under test control between our software and systems that it collaborates with. This gives us what I call measurement points for our system, places where we can provide inputs and collect outputs to make our tests realistic, but also as simple as we can get for our system. These may still be complex tests, but they will be focused only on the system that we are building. You may be worrying about the interactions at these points, and you're right, these are why people don't feel safe without end-to-end tests. But if we have thoroughly tested our system with our close to the edges acceptance tests, then all we're really interested in about these conversations now is, does A talk to us in the way that we expect, and can we talk to C as we expect? When we think of these tests like that, then we don't need lots of complex testing at these points. We need more focused tests targeted at verifying these interfaces. These more focused tests are actually better at verifying these interfaces too, than just throwing usually boring cases through the whole end-to-end system. This approach is something that I've mentioned before, contract testing. So we get to more thoroughly test our system, and we get a better, more targeted validation of these interface points. There is a step further that we can take. If we write our assumptions of how we will interact with systems A and C in the form of contract tests, we can give them to the teams A and C. They can now run our tests in their deployment pipelines. Now, if they make a change that breaks our assumptions, it'll cause our tests to fail. And they have to decide what to do next. Fix their code so it doesn't break our test, or come and talk to us about our need to change our assumptions and or our contract test. This approach is sometimes called user contract testing. The places where this approach breaks down is where the interfaces between the external systems and our system can't really be trusted, which is common in big ball of mud systems. But the real answer to this problem is to stabilize control at these interfaces. As I've said before, these sorts of places in code are more important than other places, in the sense that they will propagate problems between teams when you get them wrong. And those sorts of problems are really quite a lot more difficult to deal with when building software with lots of teams. Once we have this idea of end-to-end for our software, but not including everyone else's, we can do some smart things with our test infrastructure. Effectively, as I said at the start, building a sophisticated test rig. that our software kind of plugs into and allows us to more easily and with high levels of precision put it into whatever state we need it to be in for this test. When we built the LMAX financial exchange, this was exactly how we organised our acceptance testing. Our system integrated with 25 to 30 different external third-party systems. For each, we faked it when acceptance testing. So we could do things like this. In this example, the approve account call on accounts is priming our test infrastructure, our stub that represents an external third-party system. When our system under test makes a call to this external third-party system for, in this case, know your customer checking or similar, for a named account, we have predefined the response that we'd like it to give. So we're certain that the account will be approved. Here's the opposite case where we want to simulate a rejection. None of this is really very complicated, but from the perspective of our system under test, it doesn't know that this is all faked. This approach also means that even lengthy, complex, long-running interactions with external systems can be simulated in very short time frames, microseconds sometimes. So, as well as being more deterministic, these tests are also a lot faster than if we had a real system to talk to here. We did this at LMAX for all the time that I was there. I'm pretty sure that they're still doing it now, many years later. We ran our own contract tests against each endpoint, usually the endpoint's beta test site. And during the 5 or so years that I was there, we never had a production incident caused by a failure of our interactions with these external systems. We sometimes had contract tests that would fail against their beta site, and we'd change our integration with it appropriately. Once we understood the change, we'd do this by first changing our simulation in our tests. This is a much more controlled strategy for very thorough, very detailed acceptance testing, and is a lot more effective and a lot faster than the end-to-end alternative. Thank you very much for watching.